Welcome to Chapter 34. I'm Caleb Price. You have made it to the last chapter of physical science that you're going to be tested on. The other one is a very feel-good, good science chapter. So we're going to be talking about cosmology, which is the big unanswered questions of the universe. So let's start off with different types of galaxies. As you can see from my very pretty pictures, this one is called a spiral. For me, these are almost intuitive. If it's a spiral, it's a spiral. If it has a bar in it, it's a barred spiral. If it's a circle, it's elliptical. Elliptical. And if it looks really weird, it's an irregular galaxy. Now, there's a few things we need to know about these galaxies. Typically, based off of our observations, spiral galaxies and barred spiral galaxies have bluer stars in them. What does that mean based off our last video? That the stars are younger and hotter. Elliptical galaxies tend to have more redder stars, which means they are older and cooler, kind of an older generation. It's the old folks' home where stars live. Irregular galaxies can be anything. Irregular galaxies are formed by massive collisions of other types of galaxies or some other mechanism that we don't know about. For our next topic, we're going to be discussing something that you learned back in Unit 1, the Doppler Effect. So the Doppler Effect usually happens with sound. For example, you have a vehicle that is traveling towards you. The pitch increases as the vehicle comes towards you and then decreases as it goes away from you. Sounds like this. Cop cars do this all the time, or ambulances when they're going by. Now, it turns out that galaxies do the exact same thing. So if we're here on planet Earth, and we have our special little spiral galaxy here, if the galaxy is coming towards us, the light waves, the photons, are actually going to bunch together and become blue shifted. That means that the color of the galaxy will be shifted more towards the blue end of the spectrum. Not by a lot, just by a little bit. And if a galaxy is moving away from us, the light traveling towards us is going to spread out and be red shifted. Now, how much the redshift is, how more red it gets, depends entirely upon how fast it is moving away from us. And it turns out that because space is continually expanding in all directions and dimensions, that the red-shifted galaxies, the ones that are farther away, are actually moving faster and faster and faster. So this brings us back to how we can tell stellar distances. We got radar ranging, triangulation, brightness versus distance with that HR diagram, and finally, based off the redshift. We use the redshift to figure out how far away distant galaxies are. Because these galaxies have a proportional amount of redshift compared to how fast they're moving, which is actually how far away they are, we can then tell how far away a galaxy actually is based off the amount of red shift. Our final topic we're going to talk about is the concept of the Big Bang. This is the formation of everything in the universe as we know it. Now, this theory goes that everything started out in the universe as a primordial atom. Everything in the universe was contained within an infinitesimal speck of energy, which then randomly exploded. Before this point, we have no evidence. We don't really know what happened. This is what scientists believe. A primordial atom exploded until it eventually became our universe. Now, if you contained all of the matter into a single speck and then blew it up, how hot do you think it would be? It turns out that it was 10 to the 32nd degrees Kelvin, which is unbelievably hot. This is hot enough for fusion to take place, and it turns out that that's actually what happened. Everything blew up, and eventually, after several seconds and throughout the course of the first couple minutes of the universe, you had quarks form, and then you had protons and electrons and neutrons begin to form. These protons and neutrons began to combine together to form nuclei. It was hot enough for this to be able to happen during these first few moments of the Big Bang. So, you had beginning fusion take place. Now, it was hot enough for about 25% of all of the matter in the universe to fuse together. So you're left with an abundance of elements of 75% hydrogen and about 25% helium. And so this is going to be our first evidence for the Big Bang. Number one, the abundance of the elements. The universe is about 75% hydrogen and between 23 and 25% helium. The other 2% is everything else. iron, uranium, nickel, all of those elements. There are two other evidences for the Big Bang that we need to know. So this giant fireball that took place billions of years ago, there is probably some leftover heat from it. And it turns out that there is. It's known as the cosmic microwave background radiation. What a mouthful. So this acronym, CMBR, is an evidence that the Big Bang took place. It turns out that if you point a microwave transmitter or a microwave antenna out into space, you'll pick up this constant buzz that's at about 2.5 to 3 degrees. That's the space temperature. 3 Kelvin. So the interstellar medium, the interstellar dust, basically the average temperature of space is about 2.5 to 3 degrees Kelvin. This is leftover heat from the giant fireball that was the Big Bang. Now our third piece of evidence is a very strange phenomenon. Previously I talked about how if something was moving close to us like a galaxy, it would be considered blue shifted. Now it turns out that 99.9% of all the galaxies in the universe are actually red shifted. Everything is moving away from everything else at an increasing rate. This is consistent with a Big Bang model. There was a giant explosion, which then created an expanding universe where everything is getting farther away from everything else faster. And it's not that the things themselves are moving, it's actually space itself that is beginning to expand. Thanks for joining us for PS100.